All right, hi everybody. I'm gonna go ahead and go through number 22 from the test prep now. So this is the one that I think that a lot of you were asking about, and when I looked at it, I saw exactly why I think that that probably was a problem that you had some questions on. So this one says that we have two 4-kilogram masses that are connected to each other by a spring with a force constant of 25 newtons per meter and a rest length of 1 meter. If the spring has been compressed to 0.8 meters in length and the masses are traveling toward each other at 0.5 meters per second each, what is the total energy of the system? So for this one, if we go back to our handy dandy formula, which I just have on this little piece of paper now for convenience, what we're looking at here is basically just what is this, right? What do we have on one side of our equation? Whether this is the initial or the final, it doesn't really matter. We're just looking at what the total energy is at this instant. So for this one, we're gonna use our, let's call it a final. No, we'll call it an initial, that's fine. So here we're gonna have our spring, right? So we're gonna pull this one down. So we're gonna have 1/2 kxi squared plus, and then we have two objects that are moving here and contributing energy to the system. So the first one is gonna be 1/2 mvi squared. And then the second half is going to be the same thing. So we could just say plus 2 of these, but I'm just going to write them separately because these masses are doing the exact same thing, and that's going to equal our energy total. So now we have to kind of figure out what all of these things are. So we can plug everything in. So 1/2 times our K we know is 25 newtons per meter. And our X, this is a little bit tricky. So we know that the actual length of the spring is 1 meter when it's the rest length, so when it's decompressed. And it's been compressed to 8 meters. So that means that the actual compression that happened is actually only 0.2 meters. So that was the first tricky thing with that question. Now, for our kinetic energies of our two masses, so the masses both have 1/2 times the mass, which is 4 kilograms, times our velocities. They're both moving at 0.5 meters per second. And that's going to be squared. So we can just do that twice. Once again, you can just double this, but I'm doing it like this. Okay. So we're going to do 1/2 times 25 times 0.2 squared plus 1/2 times 4 times 0.5 squared plus 1/2 times 4 times 0.5 squared. We get 1.5. So our total energy is 1.5 joules. So there's a lot of tricky things about this one. One is the spring length thing, right, where we're trying to look at how much the compression is on the spring. And so if we're going from 1 to 0.8, then our compression is 0.2. The other one is the two masses, but each of those masses are going to be contributing their own energy because they're both moving. So those are contributing their own energy as this system is getting compressed. And we look at this specific point in time. So I hope that that helps for this one. Kind of a weird question, and I know that the solution B probably isn't the most helpful solution. So hopefully this helps you make sense of what's going on in that problem a little bit better. That's a great question, and definitely one that you should make sure you have a good sense of. All right, let me know if you need anything. Thanks.